Hi there, welcome to this short video on the scenario-based questions towards the end of your 2391 online exam. Obviously, you will need access to these 3 books. As we are running through the questions, remember, pause as we go so that you can carry out the calculations yourself. Remember, take clear notes as to where you find all this information. So we have here a circuit schedule. The circuit schedule you see there, we've been given a ZS at dB, and the circuit descriptions as well as the installation methods, number of points served, size of conductors, cable loop lengths, information on the overcurrent protected devices, and the maximum earth fault loop impedance values. So, question that might be asked is, what's the expected prospective earth fault current at the main switch to this consumer unit? So looking at the circuit schedule, you'll see there at the top it has a ZS at dB value. That ZS at dB, remember, is different from the ZE value. When we're carrying out a prospective earth fault current test, it's the ZS at dB value that we utilise for this. So we take our nominal voltage and we divide it by that ZS at dB in order to find out that earth fault current. So we take 230 volts and divide it by 0.17 ohms. And that gives us a prospective earth fault current of 1.35 kiloamps. Okay, so 1.35 kiloamperes. Follow-up question from that might be, do you need to carry out a prospective earth fault current test for the rest of the circuits? Well, if we look at the circuit schedule, you'll see there the breaking capacity for all these devices is 6,000 amperes. That 1.35 that we've calculated is clearly less than the 6,000 amperes, so it's not required to, or we're not required to carry out that prospective earth fault current downstream from that incoming supply. Okay. Remember, we have to be able to justify any live working. So another type of question you might get, what's the expected R2 value? In this instance, I've said for the cooker circuit. So for the cooker circuit, you'll see there we have a 2.5 millimeter squared CPC with a 15 meter cable length. Okay, so the run is 15 meters. In your on-site guide, table I1, or in your guidance note 3, table B1, if you have a look there, you'll see the 2.5 millimeter squared conductor on its own has a milliohm per meter value of 7.41 milliohms per meter. We take that 7.41 milliohms per meter and the 50 meters in length, and we then calculate the R2 value for the circuit. So we take the 7.41 times the 15 meters, divide it by 1,000. Why are we dividing it by 1,000? Well, this first figure here, this 7.41 is in milliohms per meter. Okay, so we're going to correct that. So 7.41 times 15 divided by 1,000 gives us 0.11 ohms. So our expected R2 is 0.11 ohms. Follow-up question from that might be, what's the expected R1 value for the cooker circuit? So if you're doing a wandering lead test, this time rather than on the CPC, this time on the live conductors, so on the line conductor here, you see it's a 6 millimeter squared conductor, again same 15 meters in length. We go back into that Appendix I or Appendix B in the on-site guide and guidance note 3 respectively, and we look at the 6 millimeter squared conductor there. You see there it has a milliohm per meter value of 3.08, and we throw that into the calculation same as we did before. So we're now looking for R1, so we take that 3.08, multiply it by the 15 meters, and then divide it by 1,000. Okay, that gives us 0.05 ohms. Follow-up question from that might be, what's the expected R1, R2 value for this circuit? Well, option number 1, add your previous 2 answers together to get your R1 plus R2 value. Okay, so we take the 0.05 plus the 0.11. That's the R1 and R2 values from the previous questions. And that gives us a value of 0.16 ohms. Or Option number 2, we can go in and look at that circuit schedule again. You see it's a 6mm squared line conductor, 2.5mm squared on the CPC, and we can carry out a calculation with the 6mm squared and 2.5mm squared conductors, milliohm per meter value of 10.49. Okay, so we use that 10.49, times it by that 50 meters, again divide it by 1,000. That gives us an expected R1 plus R2 value of that same 0.16 ohms. Okay. Follow-up question from that: what is the expected ZS value for the cooker circuit? Well, looking at the circuit schedule, we have a ZS at dB of 0.17 ohms. So we take our ZS at dB and our expected R1 plus R2 value and add them together. It's the same as doing a ZS equals ZE plus R1 plus R2. As I said, in this instance, it's a ZS at dB value we're utilising. So that gives us 0.17 plus 0.16, gives us a ZS of 0.33 ohms. Okay. Follow-up question from that might be, does this meet its requirements for its earth fault loop impedance value for automatic disconnection of the supply? So looking back in the circuit schedule, you'll see there we have a max ZS of 1.09 ohms. Okay. Now that max ZS from BS7671 of 1.079 ohms is at 70 degrees C. Remember, we are measuring our maximum ZS at 20 degrees C, so we need to bring our max value from 70 degrees C down to 20 degrees C. So we use this factor of 0.8. Where do we get that from? Well, copper has a positive temperature coefficient of 0.004 ohms per ohm per degree C at 20 degrees. And our calculated values that we've been utilising in the tables on the previous examples were all at 20 degrees C. So we need to bring that max ZS value down to 20 degrees. So we take that 1.09 and we multiply it by 0.8. That gives us a max measured of 0.87. Our expected ZS from the previous calculation is 0.33 ohms. So looking at this, we can see that 0.33 ohms is less than the 0.87 because that's the max value. So we know that passes. Follow-up question from that: what's the expected R1 plus Rn value for the cooker circuit? Pretty straightforward. We're dealing with the live conductors here. So we have a 6mm squared line and a 6mm squared neutral conductor, both 15 meters in length. Again, we get into that Appendix I in the on-site guide, or Appendix B in the guidance note 3, and we'll look down the table for the 6mm squared conductor 1, conductor 2. Okay. Values, and we get 6.16 milliohms per meter. So 6.16 milliohms per meter in the 15 meter length, we pop that into our calculation, same as we've carried out previously. So 6.16 times 15 divided by 1,000 gives us an R1 plus Rn value of 0.09 ohms. Follow-up question from that: what's the expected volt drop on the cooker circuit if the maximum demand is 34 amperes? This one's pretty straightforward. We have our R1 plus Rn value, but remember that's at 70 degrees C. So we need, sorry, it's not at 70 degrees C, it's at 20 degrees C. We need to bring it up to 70 degrees C. So as a result, we take that R1 plus Rn value and we multiply it by 1.2. Why? Again, remember our expected values are at 20 degrees C. We have a factor of 0.004 ohms per ohm per degree C for the cables positive temperature coefficient. So when we're going from a measured value of 20 to 70 degrees, we're increasing it by 50 degrees C. So we multiply it by that 1.2, because 50 times 0.004 gives us a factor of 0.2, same as in the previous example. We reduced it by that same 0.2 factor because 50 times 0.004 gives us 0.2 again. Okay, so 0.9 times 1.2 gives us a value of 0.11 ohms. Okay, so the R1 plus Rn value at 70 degrees C is 0.11 ohms. Now remember, this is not a final answer, this is just a step towards that final answer. So the volt drop, we take that R1 plus Rn value at 70 degrees C and then we multiply it against the design current. So that 0.11 times, times 34 amperes gives us a volt drop of 3.74 volts. Okay. Right. As a follow-up from that, they might then ask you, does this meet the maximum allowed volt drop for the circuit? Well, the maximum volt drop for this circuit is a cooker circuit, therefore it's not a lighting circuit, so we use 5% of the nominal voltage. So we take 230 volts and we multiply it by that 5%, 0.05. That gives us a maximum volt drop of 11.5 volts. Our expected volt drop is 3.74 volts. Therefore, again, less than that 11.5 max. So the circuit passes. Okay. So that's just how we run through and how some of those questions might join together. Okay. You see we have other circuits. We've got shower circuits with 8.5 kilowatt load. We've got a ring final socket circuit. Generally, you'll find most sockets, ring socket circuits, will say that the expected demand on these are 20 amperes. Yeah. Okay. They might give you specific loading on the lighting circuit. For the socket circuits, you'll see there it's giving you, also says there ring loop length, so they might ask you to calculate the little R1, little Rn, little R2 loops on the ring final socket circuits. They might ask you to do a stage 2 and stage 3 expected value calculation, where you're calculating the R1 plus Rn or the R1 plus R2 values, and then it's pretty much the same format as we've had in the previous questions. So hopefully that's helped you in your learning journey. If you're running into any difficulty, you know how to get in contact with me. As I said, there are plenty of examples for this in your Kahoot quizzes, and it should hopefully help you get up to speed for the online exam. Onwards and upwards, folks.